Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and I suppose I think I have three people there that were waiting for this particular live stream. So I just wanted just to check, just to make sure. I'm just gonna just check to make sure you can hear me okay, and that you can see my hands moving on this particular work area. So I'm just gonna ask, I suppose, first of all, can you hear me okay? That's just a question there, and that will also allow me to determine, I suppose, who has joined us, who has joined us there today for this particular session. The session is another live stream in our series of videos, our series of live streams dealing with hypothesis testing, and in particular, what I'm going to have a look at today is what's known as the chi-squared. Good, there's many chi-squared tests that we can actually undertake. Yeah, there's three important categories of tests, I suppose. There's what's known as the chi-square goodness of fit test, where we check to see whether a set of observations from some experiment, whether they fit a particular predefined distributional shape, okay, distribution. Another version of the chi-square test is what's known as the chi-square test of independence. This is allowing us to test whether let's say two variables exhibit dependence or independence between them. So I'm going to have a look at them two today. We can also use the chi-square test to test for the significance of a variance, a single sample test of a population variance. And we also use chi-square for many other things. But for us today, we're just going to look at the goodness of fit. So hi, Grania, that's great. Yes, we can hear and see you clearly. Brilliant. Amit, yes, I can hear you also. Brilliant. Okay, so thanks very much for joining us. And I suppose let me just get started here. I'm going to look at the goodness of fit test first of all. But what I'm just going to pull out of Sky is the test statistic. Yeah, and the test statistic is the same test statistic that's going to be applied to either one of these tests. And our test statistic looks something like this. And we'll just have a look at the test statistic. It follows a similar, let's say, makeup with respect to all test statistics, that it's going to be measuring distances effectively. But what the test statistic allows us to do is it counts frequencies, the frequencies of occurrence of particular events, and it looks at observed frequencies relative to expected frequencies, and calculates the distance between observed frequencies and expected frequencies. But don't forget, anytime we calculate distances, we're always calculating, I suppose, let's say squared distances, yeah, because we don't want to be dealing with the overhead of negative value. So we're always calculating squared distances, yeah. And these squared distances are always, this distance now is always relative to what we expect. So it's going to be relative to an expected frequency. So effectively, a chi-square test statistic looks something like this, and it's summed up over all observations. So for every single observation, we count how many times the observation occurs. Uh, we have hypothesized our expected frequency, how many times we believe it should occur. So when we take the observed away from the expected, if there was no difference between what we have observed and what we've expected, well, then two numbers should be the same, and hence this numerator should be 0. And when we divide by the expected, we should get 0. And if this is true for all observations, if none of the observations deviate from where we expect them to be under our null position, well, then the summation here is effectively 0. So this particular statistic we call the chi-squared statistic. Okay, this particular statistic has a minimum value. It has a minimum value of 0. Okay, has a min. Okay, so the min of chi-squared, yeah, okay, is equal to 0 when there's no difference. Okay, when what we've observed fits what we expect. Okay, and similarly, when it comes to the test of independence, if the two data sets are independent of each other, yeah, uh, we also get a minimum value of 0 for the test statistic. So let's have a look at the goodness of fit example. Okay, and let's just try to motivate this by considering a particular scenario. Okay, so let's consider this scenario. Okay, and the scenario is that you're in Las Vegas. Okay, you're in Las Vegas. And you're on the craps table. Okay, you're using die. Okay, so you have some dies that you're going to be rolling. Okay, and they have specific face values and so on and so forth. Okay, and you want to determine whether the die is, let's say, biased In other words, is the die rigged or is it a fair die? So that's the question that we're really asking. Yeah. Okay. Is the die, is the dice, is the dice fair? Okay. Now, if we think about this here for a moment, yeah, the face values of a die, yeah, the face values, okay, let's say the face on a die, uh, well, the face values are 1, 2, 3, 4, 5, and 6, okay? And if the die is fair, we'd expect each one of those face values to appear with a certain probability, okay? And if it's in fact, if it's fair, we'd expect to see a 1. Oh, sorry, that should be a 6 there, not a 7. What am I saying? Okay. Okay. We'd expect a 1 to occur. Well, it should occur 1/6 of the amount of times when we roll a dice. So we'd expect the probability of observing a 1. Okay. So the probability, okay, of observing one of these values, okay, well, it should be 1/6 of the time we should get a 1, 1/6 of the time we should get a 2, 1/6 a 3, 1/6 a 4, 1/6 a 5, and 1/6 of the time we should get a 6. And this is the distribution. Okay, this is the probability distribution associated with rolling a fair die. Okay, where everything is as equally likely to happen as everything else when it comes to the actual events when we roll a die. Okay? So we want to test a scenario. Don't forget, we're in Las Vegas, and let's say, for example, let's say we roll. Let's say we roll. I'm just going to get rid of that. Sorry, my apologies, guys. Okay, I'll just mute my phone. My phone is. I just got rid of that there. Okay, that's gone. I'm just going to mute my phone. Sorry, guys, just bear with me. My apologies there. That's muted now. Okay. So let's say we roll a die, a die, a dice. Yeah. Let's say we roll it. Let's say 1,000 times. Okay. So we roll a dice 1,000 times in Vegas. Okay. And we want to check to see whether the die is fair. And let's say what we observed. Okay. What we observed. Okay. When we rolled the die with respect to the face values, 1, 2, 3, 4, 5, and 6. What we observed. So here's our observations. We observed that the 3 occurred 200 times, the 4 occurred 200 times. Okay, let's say the 1 occurred, let's say 100 times, the 2 occurred 100 times. Okay, that gives us 2, 4, 6. Let's say this occurred 300, the 6 occurred 300 times, and let's say the 5 occurred 100 times. So the question we have now is this evidence, okay, is this evidence to suggest that the die actually is in fact fair? Okay, so let's just make sure that the total number of observations here is 1,000, because we're meant to roll the die 1,000 times. So we have 304, 6, 8, 9, 10, which gives us 1,000 observations. Okay, so we want to figure out now whether this die is fair or not. Okay, after we roll it 1,000 times. So what we're going to do is we're going to use this test statistic to try to figure this out. Okay, but first of all, what we're going to build is we're going to build a table that has our observed frequencies. Okay, here's our observed frequencies here. Okay, and our expected frequencies. What we'd expect to happen if we actually did roll the die 1,000 times, and if it was actually fair. So let's just redo that table out. Okay, so the values on the die are 1 to 6. Okay, so our values are 1s to 6. So let's just say here's our table. So our values, okay, are the values 1, 2, 3, 4, 5, and 6. Okay, our observed frequencies, okay, FO, our observed frequencies with respect to rolling our die. Well, a 1 occurred 100 times, a 2 occurred 100 times, the 3 occurred 200 times, the 4 occurred 200 times, let's say the 5 occurred 100, and the 6 occurred 300. Okay, the 6 seems to be occurring a lot more than the others, followed by the 3s and the 4s, and the 1s, the 2s, and the 5s don't seem to be anywhere near where the 3s and the 6s are with respect to their frequencies of occurrence with respect to this die. Okay? So there seems to be something unusual going on with the die. I wonder, is it statistically different to what we'd expect to happen? Yeah. So our expected frequencies, okay, is, well, out of the 1,000 times that we roll the die, okay, a 1 should occur 1/6 of the times. Okay, so if you take 1,000 and we divide it by 6, what we should have is 166.6. Yeah, let's just say that's 167. 167 times it should be a 1, And likewise, 167 times it should be a 2, 167 times it should be a 3, 167 times should be a 4, 167 times should be a 5. And if you roll the die 1,000 times and it was fair, 167 of them rolls should be a 6. Now, I'm at the rounding up here, yeah? So actually, to be honest with you, I've included 1, 2, 3, 4, 5, 6 extra rolls, okay? But effectively what we have is we have observed and expected frequencies now, okay? Now, as I said, the test statistic, okay, the test statistic, the chi-square test statistic takes our observeds and takes away from them the expected frequencies. And so that's the distance between the observed and the expected. And as I mentioned a moment ago, if there was no difference between observations and expectations, well, then this difference should be 0. Don't forget, we always get square distances, okay? And these are all relative to what we expect. They're relative to the null position, okay, to the expectation. And we do this for them all. So really what we need to do is with this table, we need to calculate this particular value, the observed minus the expected squared relative to the expected for each one of our observations. So what I'm going to do is I'm going to find out what observed minus the expected is, okay? Square it and divide by the expected. I'm going to do that for everything. Yeah. Okay. So let's do it for the first one. So the observed is a 100. Okay. There we go. Okay. I'm going to take away from that 167. There we go. And what I'm going to do is I'm going to square that. Okay. So it says observed minus expected. That's what we have. 100 minus 167. I'm going to square it. Gives us 4489. And I'm going to divide by the expected. The expected is for a 1 is 167. Okay. Which now gives us that the distance between the observed and the expected is 26.8. Let's just say it's 27. Okay, it's 20. It's 20. It's 27 there. Okay. In relation to in relation to the 2, well, that's similar characteristics. The observed is 100, the expected is 67, so the difference is also going to be approximately 27. Okay. In relation to the 3, the observed is 200 minus the expected, minus 167, okay, which needs to be squared. And we need to divide that by the expected, which is 167, which gives us a value of 6.5. 6.5. And for the 4, we're also going to get a 6.5 because the observed and the expected are the same as the previous one. And for the 5, it's 100 and 167, so we're going to get 27 here. Okay. And for the 6, we have it's 300 minus 167. When I square that, that gives us a pretty big number there, 17,000, divided by the expected, divide that by 167. That gives us a value of 105.9, which is approximately 106. Okay. So now what we have is we have the magnitude of the individual differences, yeah, between the observed and the expected, yeah, the square differences relative to the expected, what we'd expect to happen. So our chi-square test statistic, okay, is the summation of all of these values here. So effectively, it's 27, 327. So it's 3 times 27 because that's 27 on this one, okay, plus there's two 6.5s, 2 times 6.5, okay, plus 106, okay, which gives us a chi-square test statistic of 200, which I know even now, just looking at this, okay, already, yeah, okay, this is a colossal test statistic. It's very big, okay, it's very big. Don't forget, just looking at this, what we're saying is if there was no difference between the observed and the expected, we'd expect the test statistic, the chi-squared, to be 0, okay? Because this number would be 0 divided by any number, and we end up with 0, and it'll always be a summation of zeros, which gives us zeros. This is a very big number. So we need to do the hypothesis test, okay, to really determine whether this value is big, far enough away from 0 to be statistically different. Okay. So what I'm going to do is I'm going to set up the hypothesis. So our hypothesis, okay. Okay. The hypothesis has a null position and has an alternative. Okay. Now, in this situation, the null position, okay, it's in relation to this what a fair die looks like. Okay. Okay. So, and the reason why I'm calling this a goodness of fit test, okay, is because this is the distribution that we'd expect to happen. Yeah, okay. And the test is whether this data, from an observational perspective, frequency perspective, we could convert these values into probabilities. Okay, so based off this, the empirical distribution, yeah, would be, well, that's after 100 over 1,000. Yeah, okay, which effectively is 1 over 10. So that's 0.1. That's 0.1. This is 0.1. This is 0.2, 0.2, and 0.3. These are the individual probabilities, yeah, based off of our empirical experiment, yeah, with respect to the individual outcomes. Now, what we'd expect to happen is a 1 divided by is a 1 divided by 6, if that makes sense, okay? Which is, we'd expect these to be 0.117 across, and what we're seeing is 0.1, 0.1, 0.2, 0.2, 0.1, 0.3, okay? So the question is whether this distribution of observations fits this distribution of expectations from a probability perspective. Okay? So just that's why it's called a goodness of fit. Whether it fits it and whether it fits it well is the real question that we're trying to determine. Okay? So the question would be then is H0 would be, okay, that it does fit. Okay, in other words, the dice is fair, is really what we're saying. Yeah, the dice is fair. Yeah, because this data fits this data here, and this is the fair situation, which is what we're going to assume. Yeah, okay. So the dice is fair. The alternative is the dice is unfair, if that makes sense. Okay. We're going to assume this to be true. We assume true, doesn't make it true. Okay, so we assume the null position that the dice is fair. In other words, what we're assuming is that the expected frequencies are these things here. Okay, the significance of the test. Okay, that's our hypothesis done. Our significance. Okay, okay. Well, it's very subjective, but we're going to set alpha is equal to 0.05. Okay, and this distribution is a chi-square distribution that we're going to use, and it's depending on the degrees of freedom, it's a skewed distribution. Okay, okay. But in this case here, all of our alpha is, see, here's 0. Here's where there'd be no difference, yeah, between the observed and the expected. The chi-squared value was down here. Okay, but we're going to put all of our alpha into the right-hand tail here. Okay, this is a one-tail test, because we're always starting at 0. We're never going to be going into the left tail. Yeah, okay, comparing, we're always going to be, all of our distances are always going to be greater than or equal to 0. So the further away we are in this direction, yeah, the more evidence there is that we've deviated away from the concept of fairness. That's fair die there. Okay, so that's our significance. So our hypothesis is done. Our significance, our test statistic. Okay, okay. The test statistic. Well, the test statistic we've actually calculated over here already. We have chi-squared is equal to 200. Okay, and now we have to have a look at our critical values. Our critical values. So what we need to do is we need to go to a table of chi-squared, the table associated with the chi-square distribution. Now, the degrees of freedom, this table is parameterized by how much area you've put in the right tail. Okay, so the area in the right tail, and also the degrees of freedom. Yeah, okay, which is how many observations we have minus 1. Okay, so it's the number of possible events, yeah, that could occur. Okay, if that makes sense. Let me find this table here. So I have a chi-square table. Okay, excuse me. I have a chi-square table here. Okay, so here's my chi-square table right here. Across this particular row here is how much area we've put in the right-hand tail. Okay, we're going to put all of our area in the right-hand tail, 0.05. So I'm in this column here. And our degrees of freedom is how many levels are there associated with this particular, let's say, with this particular process. And there's 6. Yeah, so our degrees of freedom is going to be n minus 1. Okay, so our degrees of freedom is equal to n minus 1, which is 6 minus 1, which gives us 5. Okay, so when we go to the tables, we're looking at on our chi-square tables. Okay, we're going down to column 0.05. And we're going down the degrees of freedom down to 5 degrees of freedom, which gives us a critical value with 5 degrees of freedom of 11.07. Okay, that's our critical value. So effectively, this value here, this cutoff point, is 11.07. Okay. Now, our test statistic is 200. Our test statistic is out here. It's out here somewhere. It's well out there in the tail. It's gone off into the over the horizon. That's how far away it is. Yeah. Okay. But our decision is a comparison of our test statistic to our critical value. Okay. That's when we're using the critical value approach. So our decision, okay, is, well, let's just draw that graph again. Okay? It's a chi-square distribution which is positively skewed depending on degrees of freedom. Okay? The critical value here is 11.07. This is our rejection region. Okay? And our test statistic chi-squared is equal to 200 is well in the rejection region as well out there. So clearly, the chi-squared value is bigger than the critical value. What we mean by that is 200 is bigger than 11.07, and as such, we reject. So we're rejecting here. We reject H0 in favor of HA at the 5% level of significance. Okay, level of significance. Okay, and now we can infer, okay, that the dice is in fact unfair. Okay, because we've gone to the rejection point, if that makes sense. Okay, guys, that's effectively it. So, if just happens, this test statistic was huge in this situation. Yeah, okay. I think we could see as well from our observations. Yeah, okay. I mean, the 6 occurred 300 times. Okay, it should have only occurred 167 times. And there was other instances where we were under our expectation, and other instances where we were slightly over. But this 300 was well above where it should be. Okay? And in fact, we're statistically confident now. We're 95% confident, yeah, that the die actually is in fact unfair. Okay, okay, guys. Maybe I'll just ask you now. Does that help out with that particular test, that chi-squared goodness of fit test? Okay? We could do a different distribution. We could do a distribution that has different values here. Yeah, instead of everything being equally likely, we could have our expected distribution to have different. That 6 occurs at different rates. A 3 occurs at a different rate compared to the other values. Yeah, and in fact, we use a chi-squared distribution as well to test whether a set of observations comes from one of our more flavored distributions, like a normal distribution, like a Poisson, like any particular type of distribution. We can use a chi-squared as our goodness of fit. I think I do have a video up there where we test whether a data set there's evidence that data set has been taken from a normal distribution, and we use a chi-square test for it. Okay. Okay, that's brilliant, Grania. Okay, so what I'll do now is I'll just continue on and I'll do the next test, which is the chi-square test of independence, and it still uses this test statistic. Okay. Now, for the business data analysis class, and I've seen, let's say, I've looked over many of them past exam papers. Yeah, the past exam papers primarily concentrate on the goodness of fit test. Yeah. Okay. But let me maybe just take things a little bit further and let's have a look at this test of independence. Okay, so I think what I'll do is I'll probably spend the next 20 minutes, 30 minutes, maybe just exploring that test of independence with an example. And the question that I want to try to answer is this: is there any evidence? Okay. Is there any evidence to suggest that, let's say, that the hourly rate, okay, of males compared to females is different to each other? Okay. In other words, does your hourly rate depend on your gender? Okay, there's a nice question actually to ask. It's probably quite popular and topical now. Okay, and what we're going to try to do is we're going to try to use some heavyweight statistics, yeah, to try to figure out whether that is actually true or not. Okay, if that makes sense. Oops, let me just push that up that way. Just up there. There we go. Okay, so let's consider an example. Okay, so let's say we have males. Okay, and we have females. Right? And what we have is, let's say, hourly rates. Let's say 5 to 10 euros. Let's say 10 to 20 euros, and just say for argument's sake, let's say we have 20 to 30 euros. Okay, they're the hourly rates of pay. Okay. And what we want to figure out, and I have some evidence here. Okay, hang on. So what I've done is I've gone off and I've observed. Okay, I've observed, let's say, a number of individuals. I don't know how many. Let me just make up some numbers. Yeah, and what I've observed is that there was, let's say, that there was 20 males. Yeah, that earned between 20 and 30 euros an hour. Okay, with respect to the females, there was only, let's say, there was only five in there. Okay, let's say there was 15 females that earned between 10 and 20. Let's say there was 10 males. Okay, and let's say there was 20 females that earn between 5 and 10 euros an hour. That's probably illegal. So some quantity of money. And then in relation to the males, let's just say that there was let's say 23 males. So in total, I surveyed 23 plus 20 plus 10 plus 15 plus 20 and plus 5. In total, I surveyed 93 individuals, if that makes sense. So 93 individuals were asked their gender, and were also asked how much was their hourly rate. Okay, and the question I'd like to answer is, okay, is there evidence? Is there evidence? Okay, to suggest, okay, that gender is influencing, is determining, okay, uh, pay rates. Okay? Pay rates. Okay? That makes sense. So let's just think about this here for a moment. Yeah. So we could do what's known as, let's say, we could do our marginal count. So let's just say, I wonder how many males did I ask the question to? 23, 33, 43, 53 males. How many females? 20, 30, 40, 40 females. How many people responded with 5 to 10 euros? Well, there was 43. How many between 10 and 20 euros? There was 25. How many between 20 and 30 euros? There was also 25. Okay, which gives us in total 50, and 43 gives us 93. Brilliant. And 53 and 40 gives us 93 also. Okay, so we have these marginal values. Okay, so these are observed. Yeah. Okay, so let me just get a red pen here. Okay, so this is what we've observed. Yeah. Okay. Now, the question is, what would we expect to happen? Okay? If everything was as equally likely as anything else to happen, okay, we'd expect them 93 people to be distributed across these particular categories: the male 5 to 10 euros category, the male 10 to 20 euro category, the male 20 to 30 euro category, and the female 5 to 10, the female 10 to 20, the female 20 to 30 category. We expect the 93 people to be distributed in a fair manner across those particular categories, if that makes sense. So, what would we expect if they were independent of each other? Okay, I'm wondering, if we were independent of each other, what would the probability be? Okay, of observing a male? Okay, uh, that has between 5 and 10 euros. So the null position. Let's just actually set up our hypothesis here for a moment. Yeah, the hypothesis. Okay, the hypothesis has a null position and has an alternative. Okay, so the null position is that there's independence. Okay, independence, which is important for us because this helps us to use the multiplication rule and the version of the multiplication rule when it comes to probability that relies on independence. And the alternative is that they're dependent. That's dependence. Yeah. So the null position is that gender has no influence. Yeah. That your rate of pay is independent of your gender. Okay. Whereas the alternative says that the rate of pay is dependent on your gender, if that makes sense. And we want to test this. So what would we expect to happen? Okay, well, our expectation would be, let's just draw out another table. Okay, if everything was independent of each other, males, female, okay, 5 to 10, 10 to 20, 20 to 30. Okay, well then, if everything was independent of each other, okay, what's the probability? Yeah, okay, that out of the 93 people, okay, that I'd get a male and they are paid between 5 and 10 euros, if that makes sense. So really what I'm asking now is, what's the probability that if a person was selected at random, okay, that they were male, okay, and okay, that they spent, that their pay, okay, their pay pay, okay, was equal to 5 to 10 euros. What's that probability? Okay? That's what we want to figure out, because once I know the probability, I can actually find out how many of these 93 people should be in there. Okay, so if I can find the probability of a male and a male earning between 5 and 10 euros, that's a probability which we can convert to a percentage, and then we know the percentage of these 93 that should be in that particular category. But under the rule, which we're going to assume to be true, okay, we assume true, the null position, we're assuming independence. And this is the multiplication rule. So now this becomes the probability that the person is male, okay, times the probability that their pay is 5 to 10 euros. Okay. Now hang on. The probability of being male, okay, probability of being male is, well, how many males are there? There are 43 males, okay, 43 relative to 93. So there's 43 over 93. The probability of being paid, sorry, there's 53 males. Here's the males relative to 93. There's 53 males relative to 93. And the probability of being paid between 5 and 10 euros is 43 relative to 93. So there's 43 relative to 93. So the actual probability is, right, it is 53 divided by 93, right, gives us a value, multiplied by 43 divided by 93, okay, which gives us, overall, we'd expect 26%, yeah, okay, 0.26% of the 93 to be in this particular category, okay. If your rate of pay was independent of your gender, okay. So let's just look at this for a moment and see what happened with the probabilities, yeah, okay. So what I'm going to do is I'm going to take that 0.26, yeah, okay. So if I take that 0.26 and if I multiply it by the total frequency, okay, so if I multiply that 0.26 by the total number of observations that we have, the total frequency, well then what I end up with, okay, is 0.26 multiplied by 93, okay. Let's think about this here. The 0.26 was the 53 over the 93 multiplied by the 43 over the 93, okay, multiplied by this 93. I just want to try to motivate this where we get all of this stuff from. And what you can start to see is that one of the 93 is cancels out here. So we're left with 53 times 43 over 93. And this is our expected frequency, because that's what we'd expect to happen. So our expected frequency, yeah, is, well, what is it? For this cell here, okay, the expected frequency, okay, is the row total, yeah, multiplied by the column total, okay, relative to the total amount. Okay. So now we have a way of calculating our expected frequencies. So we can actually calculate all these expected frequencies now by just looking at, just observing where's the cell. This cell is on row 1, column 2. 53 multiplied by 25 relative to 93. Row total times column total divided by total. So we effectively have our formula now, if that makes sense. Yeah. Well, the chi-squared formula is still the same, right? Okay, but we have a way to calculate our expected frequencies. Yeah. So our expected frequencies. Sorry, maybe I just want to just fold this over so that I can actually do these calculations. I can actually see the table. Okay. So let me just put this table here for a moment. So what we're going to do is we're going to do all of our expected frequencies. Okay. So let's call this cell A, B, C, D, E, and F. We're going to do all these expected frequencies. So for cell A, we know that its expected frequency is the row it's on, which is 53, multiplied by the column it's on, which is 43, divided by the total amount, which is 93, because that's what our expected frequencies are. The row total times the column total divided by the total amount. Okay. For column B, okay, the expected frequency is the row it's on. Well, it's on row 1, so it's a 53. What column is it under? It's under column 2, so it's a 25 relative to the total amount, which is 93. Row C, sorry, position C here, its expected frequency, what we'd expect to happen. Well, it's still on row 1, which is 53. It's in column 3, which is 25, relative to the total, which is 93. This value here is is cell D. Its expected frequency is, it's row 2, which is a 40. It's column 1, which is a 43 relative to the 93. And then we have cell E. Its expected frequency is, it's on row 2, which is a 40, times column 2, which is a 25 relative to the 93. And then finally we have F. The expected frequency is in F is, it's row 2, column 3. So it's row 2, which is a 40, okay, multiplied by column 2, which is a 25, okay, and divided by 93. Okay? So they're all of our expected frequencies. So let's just do what we'd expect to happen. If there was independence, the first one should be 53 times 43 divided by 93, should be about 25 times. Okay? Uh, if it was under the null position, okay, that they're independent for here, for males that are on 10 to 20 euros, we'd expect to see 53 times 25 divided by 93. We'd expect there to be 14 people in here. Okay. If the expected for row C, okay, it's 53 times 25 divided by 93, gives us a value of also 14. Okay. 40 times 43, so 40 times 43 divided by 93 gives us a value of, it's about 18. Okay. And these two are the same here, so it's 40 times 25 divided by 93 gives us a value of about 11, and this is about 11. So now we have our observed, we have our expected. Okay, here's all of our expected. This is, we'd expect to be 25 in here, 14 in here, 14 in here, 18 in here, 11 in here, and 11 in here. That's what we'd expect to happen. So now we can use our test statistic to calculate the observed minus the expected. Observed minus the expected squared over the expected. And we're going to do that for all the cells. Yeah, so we're going to sum that up for all the cells, which is our chi-squared test statistic. So let's do our new table. Our new table, we have males, we have females, we have 5 to 10, we have 10 to 20, we have 20 to 30, right? And let's just say we have, so what I'm going to do now in here is I'm just going to go ahead and calculate this value for each one of these particular observed. These are now our expected frequencies. These are our FEs, whereas these guys up here are our FOs are in this table, and these are our FEs. Okay. So our first one that we have, okay. So the first one that we have here is, so we've got observed minus expected squared. So the first one is going to be 23. Okay. So 23 minus 25. So we have 23 minus 25 square root divided by the expected, which is divided by 25. Okay. Gives us a value of 0.16. Okay. So we'd expect 0.16. Yeah. Excuse me. Right. We expect 0.16 of the observations to be in here. Okay. What about in here? What would we expect to happen? Yeah, under independence. Yeah. Okay. Well, we have observed minus expected divided by the expected. So it's 10 minus 14 to be squared. That gives us 4 to be squared is 16, divided by the expected, which is 14. Okay. So we said it's 10 minus 14 gives us minus 4. Minus 4 squared is 16. And 16 divided by 14 is equal to, it's equal to 1.14. Okay. So 1.14 here. What would we expect in here? Well, it's the observed minus the expected. Okay. So it's 20 minus 14 divided by 14 gives us a value of 0.43. Okay. What would you expect to happen in here? Well, it's 20 minus 18 gives us 2. 2 squared is 4. 4 divided by 18 gives us a value of 0.22. Okay? So 0.22. Okay? What would you expect to happen in here? Well, it's 15 minus 11. So it's 15 minus 11. Okay? And we square that, gives us 16. And divide that by the expected, which is dividing that by 11. Okay? Gives us 1.45. Okay? And then finally, this cell here, we've observed 5, we expect 11. Okay, so we have 5 we have 5 minus 11 gives us minus 6. When we square it, it gives us a value of 36, and when we divide that by 11, it gives us a value of 3.27. 3.27. Okay? So that's these individual values. So the chi-squared value itself is going to be the sum of all of them. So the summation of all of these values is our chi-squared. So we have 3.27 plus 1.45 plus 0.22 plus 0.16 plus 1.14 plus 0.43, which gives us a value of 6.67. So 6.67. So our chi-squared test statistic is 6.67. And now the question we should have is, how big is that? Is that big enough to be different? Okay. To be different to what? To be away, see, it'd be 0. If there was no difference, we should have zeros here between the observed and the expected. Yeah. Okay? So let's do the hypothesis test now. So the hypothesis test itself, right? Excuse me, I'm just setting this up here. So our hypothesis test has a hypothesis, okay? And the hypothesis, the null position, and the alternative. Okay? The null position is independence. That's what we assume. See, that's what we use when we're calculating our probabilities. We use the concept of independence to help us calculate these probabilities, yeah, for our expected. And then we have dependence, yeah. Okay? So the concept is that your rate of pay is independent of your gender. That's the null position. The alternative is that your rate of pay is dependent on your gender. Now we have the significance level. Okay. Well, we have alpha is equal to 0.005. Okay. So 5%. Once again, this is a one-tailed test. We have our test statistic. Okay. Now we've done it. Okay. Its chi-squared is equal to 6.67. Then we calculate our critical values. Okay. Values. Okay. Well, it's a chi-squared distribution. It's positively skewed. Okay. 0 would be independent, yeah, because observed and expected will be the same. We get 0 as a test statistic. So the further away is from 0, the more evidence there is that there's dependence between them. And we're going to put all of our alpha in this tail here. But our degrees of freedom in this case, because this is a contingency table with 2 variables, the degrees of freedom is equal to the number of rows minus 1 times the number of columns minus 1. Okay. So in our situation, the degrees of freedom, there's 2 rows, so it's 2 minus 1. There's 3 columns, so it's 3 minus 1. So our degrees of freedom for this particular test is 1 times 2, which gives us 2 degrees of freedom. Okay. And now also what we have, yeah. So now we have our critical, we have our degrees of freedom. So now we go off and look up our tables, okay, our chi-square tables. The degrees of freedom is 2, and how much area we're putting 0.05 in the right tail. Okay, and we're going to triangulate in. Okay, these are chi-squared tables. Okay, and when I get my chi-squared tables up here, once again, here's my chi-square tables. I know this is hard for you guys to see, but I have got 0.05 in my right tail, and I've got 2 degrees of freedom, which gives me a critical value of 5.991. So this is 5.991. Okay, so this is 5.991 here. And our test statistic is 6.67, which is up here. 6.67 is our chi-squared, which is bigger than the 5.991. So our decision, okay, is clearly, okay, our chi-squared is bigger than our critical value. What we mean by that is 6.67 is bigger than 5.991. And as such, we reject, because now we reject H0 in favor of HA at the 5% level of significance. Okay? And we now infer that salaries, rates, hourly rates, okay, are dependent, okay, on your gender. Okay? So, and we know that with 95% confidence in this particular case, yeah, that based off that particular scenario, okay, where we have that amount of women, that amount of men earning these particular rates, okay, there seems to be an imbalance. There seems to be your gender is influencing your rate of pay. You can see that more men are being paid at the higher rate compared to the women. A little bit more balanced here and more balanced at the lower rates, but at the higher rates there seems to be more men than women. Okay, so the advantage seems to be towards the males. Yeah, okay. But I mean, there's an unusual. This is, I believe, an unusual application now of a hypothesis test. It's scientific in the sense that it's all based off evidence and measurements. Okay, and what we've actually shown is we've shown that that rates of pay does seem to be dependent on your gender. Okay, guys, I'm just about to wrap up here now. So once again, this was Jonathan Lambert with the Mathematics Development and Support Service at National College of Ireland. I hope that this video was intuitive, and I do hope it was helpful to you. And maybe I'll just pass over to you guys now. I suppose I was going to ask the question. KG is there, and as he said, both were very helpful. Okay, brilliant. Celine, really helpful. Thank you. Thanks, Celine, for that comment. So guys, once again, thanks for tuning in. This video I think takes probably about 10 minutes just to process. Once it's processed, it'll be automatically up on the maths and stats page, and you'll be able to rewind through it to look at different parts of it and so on. But I think the main thing about this, thanks Grania, brilliant. I think the main thing about this is that we've covered two types of chi-square tests. I did say that in the past exam papers for the business data analysis guys, they're more than likely what I've seen as good as the fits. But look, we've done the test of independence now. You can see the process is the same, just with one or two slight modifications. So guys, I hope that this was helpful, and thanks for watching. Okay, bye. So I'm going to end the stream now, okay, unless there's any questions. Okay. YouTube doesn't really tell me here if anybody is typing. Yeah, okay, they should really probably change this so that it's like, like WhatsApp or maybe like Facebook, when people are typing, that picks up. Celine, the way you've answered the question, is that a good way to answer it in the exam? Yes, Celine. If I was to make one small comment in relation to that, okay, is that so I've been trying to really tell a story and to bring it on a journey, if that makes sense. But I think what would be important in the exam, yeah, is to get straight to this table. Your table has your values, has your observed, has your expected, and then it has your chi-squared individual values, if that makes sense. So to get straight to that table, yeah. Okay. Also, then in relation to the other one, which I didn't really do a table, yeah, is that I think what would be good is you do this table is given. You do this table up, and then you do the next table, the third table, if that makes sense, in relation to the observed minus the expected squared relative to the expected. So I get straight in to calculate the magnitude of the test statistic effectively. But the hypothesis test itself is always a 5-step process. Okay, the hypothesis is always going to be hypothesis followed by significance, followed by test statistic, followed by critical values, and finally followed by the decision that you actually make with respect to the comparison of the evidence as measured through the test statistic compared to the critical value. So Celine, yes, that's the way I would be setting out an exam. Sometimes in exams they ask you to state the significance level before they ask you to do to do different things, or they might ask you to calculate the test statistic before they ask you to set out the hypothesis. But that's everything in one go from a hypothesis test perspective. Okay. Is there any other questions there? Okay. Thanks, Celine. Okay, brilliant. I'm happy enough there myself. I think what I'll do now is probably a nice time. It's coming up to 50 minutes now. Yeah, I'll probably just close this and end the stream now. Okay. So once again, guys, thanks for watching. Okay. Bye. Chat soon.